Hola, chaps. Let's learn. I've taken a clear, square plastic container, emptied it of its regular contents, washed it out with some water, added some water to it, and put in a long bolt. So, what you are looking at is the interface between air and water inside this clear plastic container. And it appears as if the bolt were discontinuous. In the air, it seems to be going up and to the right, and underwater, it seems to be shifted to the right a bit before it goes down into the water. Now, you know, when you pull the bolt out of the water, it's not really broken, and the question is, why does it appear that way? Once upon a time, there was a king who was troubled by this and offered a prize to anyone who could explain why it looked like this. Eventually, one man claimed the prize. His last name was Snell, and I'm now going to try to teach you the concept of how he worked out what we now call Snell's law. So I have a story to share with you. Imagine if you were to go down to the beach and enjoy being down there, and you go out swimming into water. Here you are, and you decide, oh, the lifeguard is quite attractive. You'd like to have the lifeguard come rescue you. So you start explain, expressing that you are in distress. Help, help, hoping that the lifeguard will come to you. So the lifeguard is on the beach, which of course is, sand, and he's standing on it. This is a top-down view. This line here is the boundary between land and water, between the sand and the water, the boundary. So you would call it the shore. Here's you out in the water a little bit. Here's the lifeguard. Now, the question I pose is, what is the fastest route for the lifeguard to get from where he is to where you are, or she? So the usual answer I get from students is, well, the shortest distance would be the best answer. And so they would say, draw a straight line from the lifeguard to you, and that would be the shortest route and therefore the fastest route for the lifeguard to get to you. Let's say him and you as her. However, you're not taking into account the fact that you can't swim as fast as you can run. So I'm going to use an arbitrary number and say, suppose it turns out that the speed at which you swim, VS, is 1/5, let's say, of the speed at which you can run. So I'm using V sub R for the speed at which you can run, V sub F at the speed at which you can swim. I'm talking about the lifeguard. And you run 5 times faster than you can swim for the same distance. So whether it's meters per second or miles per hour, let's say that you can run 5 times faster on the sand than you can swim through the water. In that case, students usually think about it and they decide, okay, so the fastest way is to swim the least distance. And so they draw a line that's perpendicular from you to the shore. And actually, I have some students, I'll share this with you because I teach this every year, right? I have some students who say, okay, and then make a straight line into the shore once you are directly across from it. So they have you go way over here. I guess I can show up here, way over here, and then do a right angle turn and run straight towards you and then swim to you. And now they get to you in the least amount of distance for swimming. I actually have students suggest that each year. But you, of course, came up with something even better than that already, I'm sure. And you would say, yes, have the least distance that you have to swim in the water, but no, don't go at a right angle, cut off that triangle, turn it into a diagonal, a hypotenuse that goes like this. So You run, the lifeguard runs from starting position to the point directly across from where you are across the boundary here, and then swims. And sure enough, the lifeguard swims the shortest distance to get to you. This is almost, but not quite, the best answer. There's a faster way for the lifeguard to get to you. And no, I'm not cheating. I'm not saying, well, use the Jeep and drive over. I mean, given the conditions, running, swimming, the fact that you run 5 times faster than you swim, but not infinitely faster, is a hint that says there is a slightly faster route. And the route is not the straight line distance. It's not the least in the water distance, but it's a magical point just somewhere between them. Because you run 5 times faster than you swim, the ideal distance is going to be fairly close, relatively, to this perpendicular distance here, but not quite. I'm going to draw an approximation to it that says, okay, you run to this point after you, well, you swim there after you run to this point. And it's very hard for me to explain it, but I will try zooming in tremendously on that little intersection there and try to give you the concept that goes, you run 5 times faster than you swim. So if I were to draw a little teeny tiny right triangle, which I wouldn't be able to draw here I've increased the distance that I have to swim by a little bit. But I save more than 5 times that distance in how far I have to run. So this perpendicular distance here compared to that perpendicular distance there, which I can't draw very well, if I could sketch it to scale and do the math right, I would be convincing you, as skeptical as you might be, that there's this magical spot here, mathematically, we can calculate where it is, where you shorten the distance that you run on the sand by 5 times the distance longer that you swim through the water. And so the trade off is overall, the total distance that you run is longer than the straight line distance, not as bad as this, but it's the least time to get from lifeguard to you. Okay. So what we're doing is we're in the limit. This is 5 times different in length than that. But up until then, so if I'm here, then it's not as good. There, it's not as good. There's this optimal angle at which you get from lifeguard to you in the least time. This is the analogy to how light behaves when it goes between substances of two different densities. So the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. And that is great. And that's for all electromagnetic radiation, radio waves, light waves, gamma rays, X-rays, the whole spectrum. But when light goes into a substance, it slows down a bit. And there's actually a formula on our reference sheet, which I didn't have handy, so I guess I won't share it with you. I'll just write the formula itself. It's called the index of refraction. And it's equal to the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second squared, divided by the speed of light in that substance. So the speed of light is in the numerator, and it's the fastest that light can travel. So the index of refraction is a ratio of two speeds. Therefore, it is a dimensionless number. It's like saying, oh, she runs 3 times faster than he does. Okay, there's no units there. It's just a ratio. So index refraction is a dimensionless number, and the ratio has to always be 1 or greater. It would be 1 if we're comparing the speed of light in a vacuum to the speed of light in a vacuum. For air, the speed of light slows down ever so slightly, not by much. The index refraction for air is something like 1.000293. I think that's what I measured in my college physics course. So pretty darn small ratio. This is the amount by which the speed of light slows down compared to when it is in a vacuum. And in water, the ratio is much larger, more like 1.33. So this means it slowed down significantly when it goes from air into water. And as a result, the angle that it makes going from air into water can change noticeably. And that's what's going on with this nail in this liquid bottle here. So we started off zoomed in so you could see that well. I left it there as a prop. Snell's law works out as 4 terms in it. If this were not a person running on sand and then swimming through water, but instead a beam of light traveling through air, passing through a boundary, and entering underneath the surface of water. Okay, so Snell's law says there's the index of refraction that you start off in, and I'll just label that n sub I for right now. And then there's the index of refraction of the substance that the light goes into. N sub R I'll use for refracted material. So you measure the angle that the ray of light makes from the normal. I remind you the normal is the perpendicular to the surface of contact in physics, and the normal to the boundary is just called the normal. So if the ray of light were hitting at this point on the boundary, I take a protractor, for example, and the normal is perpendicular to it. I could crudely draw it here and say 90-degree angle. That is the normal to the surface. So with my protractor, measuring this as 0 degrees, I measure around till I get to the angle of incidence. So the sketch that I had says on my protractor, it was something like approximately 27 degrees or so is what it reads on the protractor. And let me change the lighting just a little bit, maybe even shut this off, if that helps. Now you can see the protractor. So here it's talking about an angle less than 30 degrees, but that's not the normal. That's measured from the boundary going up to here. The normal would be the complement of that angle. And so on my sketch, I would have to say, oh, my normal was an angle of incidence of 70 some odd degrees, maybe 73 degrees or so. Okay, so the normal is always measured from the boundary. The angle of refraction is also measured from the boundary and the normal to the boundary. So going off at the normal in this new substance would be the 0 degree direction, the way I have my pen pointing. And 2 things to notice. When it goes from one material to another, it always crosses it always crosses the normal, I should say. It always crosses the normal. So here it's starting on the left and it's going to leave going off to the right. Always crosses the normal. When it goes from a lower index refraction to a higher index refraction, the angle always becomes smaller. So in this example that I sketched, you can sort of imagine I sketched an angle that looks sort of like 10 degrees visually. Okay, so that's why I drew the arrow bending, the ray bending towards the swimmer, bending away from the normal. So here is Snell's formula then for calculating at what angle would a ray of light move if it came in from, let's say, air going into water at some given angle. The formula is n of the incident, so the angle of index of refraction of the incident material, times the sine of that angle. So you'd need a calculator. It'd have to be set in degrees. And you're measuring from the normal, not from the boundary. So if it's going straight in, perpendicular to the surface, we would say its angle of incidence is 0 degrees, not 90 degrees. All of that is on the outside or the first material. On the other side of the boundary, in the new material, it's the index of refraction of this second material times the sine of the angle of refraction in that material. So this is Snell's law. So there's really two equations in this little video clip. One is the formula for calculating the index of refraction if you were given the speed of light in that material. And the second one is given any three of these variables, index of refraction, angle of incidence, index of refraction, angle of refraction, solve for the one unknown. I can't really, do a calculation justice that shows what the optimal angle is for this lifeguard to get to the swimmer. Too complicated for me to figure out. But I can make up a problem and say, what if this were air and if this were water and if the angle of incidence really were 73 degrees, let's say? Okay, so the index of refraction of air, I already mentioned, is 1.000293. And by the way, it's going to work out in this unit. If you round that off to 1, that will be precise enough for your homework calculations. So unless it's a super precise problem that we're doing. And let's say that the angle of incidence were 73 degrees, as it had been in my sketch, that this is going into water, which has an index of refraction of 1.33. And see, that's already rounded off way more than it was for air. And my one unknown is, so what would be the angle of refraction? Take a moment with your calculator, pause this video, beat me to the punchline. All right, here we go. Oh, I guess I could do one more step for you. And that is, we're plugging this into Snell's law. Our unknown is the angle, but this has the sine of the angle. So what you're going to have to do is take the inverse sine of everything else. Let me first rearrange the equation and write the sine of the angle of refraction is equal to the index of refraction for the incident material times the sine of the angle of incidence. Take that product, divide it by the index of refraction in the new material that you're going into. And last of all, you're going to have to get the angle by taking the inverse sine of all of that. So inverse sine of ni sine theta I over sine theta, over n sub r. Okay, now beat me. Of course, you should check your calculator, make sure it's set in degrees, not radians. Beep, beep, beep. All right, so I get an angle of refraction of, my calculator says 45.99150.571. So of course I would write down 46 degrees. We're not going to be super precise, maybe at most to the nearest tenth of a degree with this sort of work. Yeah, probably about that at most. So there is an example of Snell's law. It explains the index of refraction when you go from one substance to another. I'm going to pause this for a moment. I paused it so I could find the reference sheet. So here it is. The Physics and Chemistry reference sheet from June 5th, 2019, page 1. If you were to bother zooming in on it, which I'm going to do, let's see, where is that equation? Huh. Oh, it's, nope, yeah, here. Okay, so if I were to zoom in, here is Snell's law. It says we might have more than just two materials. We might go from material 1 to material 2 to material 3 to material 4. Oh, imagine that a beam of light starts off in air, goes through clear plexiglass into an aquarium. So it goes from air to plastic to water to, and then reflects off a fish, and then goes from the water to the plastic out to the air. So you could have a whole stack of different substances. So for the first substance, whatever you start off in, that index refraction times the sine of the angle of incidence is equal to the index refraction of the next material that you're adjacent to times the sine of the angle of refraction in that material. Here is the formula for calculating the index refraction. It is equal to the speed of light in a vacuum, 3.00 times 10 to the 8th meters per second, divided by the speed of light in that material. Now, on this reference sheet, it happens to have the table showing the indices of refraction for various substances. So again, in a vacuum, it's exactly 1. In air, 1.000293. In water, you can see there's actually a fourth significant digit here, 1.333. And then other substances. And these are basically sorted in order of increasing index of refraction as you go to higher materials. One of the reasons why diamonds sparkle so much is because the light that goes into it from the air is strongly bent and reflects inside the diamond before it can escape from inside the diamond and come out and twinkle in your eye. So the top of the list, or if you like, this end of the list is for silicon, and it has an index refraction greater than 4, which would mean the speed of light in silicon is less than 1/4 the speed of light in a vacuum. So instead of being 3 times 10 to the 8th, oh man, it would be less than 1 times 10 to the 8th meters per second. In fact, even in mercury sulfide, that would be less than 1 times 10 to the 8th meters per second. So slowest to fastest. All right, this concludes this little section about Snell's law. Ciao.